This photograph of a mid-century practical mathematics class captures a universal experience, staring at a chalkboard, trying to memorize the rules of trigonometry. Most students rely on SOH-CAH-TOA to survive introductory exams. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. These mnemonics reduce complex mathematics to a simple memory test, focused entirely on dividing one side's length by another. Standardized testing often obscures the origin of these formulas. They were originally engineered to solve physical problems that were otherwise impossible to calculate. In the ancient world, builders and thinkers faced a massive logistical hurdle. They needed to measure the distance to, or the height of, objects they could never physically reach with a scale or a rope. Take this photograph of the 3 stone pyramids in Giza. To calculate their heights without climbing them, Egyptian builders analyzed the geometry of their shadows. This method of calculation using sightlines allowed for the navigation of the open sea. As we see in this image of a naval officer using a sextant, sailors tracked the movement of celestial bodies by measuring angles against the horizon. Early trigonometry functioned as a practical engineering workaround for the limits of physical measurement, allowing humans to map out a universe they could not touch. Watch this animated diagram. As the right triangle scales up dramatically in size, the counter on screen shows that the ratio between its sides remains exactly identical as long as the internal angle stays the same. This consistency allowed early mathematicians in Greece and India to calculate constant values for specific angles, creating the first reference tables for the sine and cosine functions. By the 13th century, scholars like Al-Tusi had fully separated these tools from their astronomical origins, establishing comprehensive proofs for all 6 trigonometric functions as an independent discipline. By isolating the relationship between angles and side lengths, they created a universal toolkit capable of calculating the dimensions of any triangle in existence. In the unit circle, the radius is exactly 1 unit, and the triangle's hypotenuse is pinned to the center. As it spins 360 degrees, watch the vertical opposite line grow, shrink to 0, and extend downward. Mapped horizontally, this traces the sine wave. Because the circle can rotate indefinitely, the wave it generates repeats in a predictable cycle forever. This rotation provides the mathematical template for anything in nature that oscillates, from a swinging pendulum to a vibrating string. That geometry translates directly to the physical world. In this photograph of draftsmen drawing technical engineering plans, they are translating angular mathematics into the physical forces required to build infrastructure. Engineers account for overlapping physical stresses, like the downward pull of gravity and the sideways shear of wind, by breaking them down into distinct angular forces. This image of ironworkers standing on high-altitude steel beams demonstrates the result of those calculations. Resolving those angular forces on paper ensures the vertical steel remains stable under pressure. We see the same principles in this photograph of the Golden Gate Bridge under construction. The tension required for those massive suspension cables is determined by the geometric angles they form with the bridge's towers. The resolution of these trigonometric forces is the primary mechanism ensuring our physical safety in the modern built environment. Beyond steel and concrete, the sine wave derived from the unit circle acts as the heartbeat of modern technology. Electrical engineers use Fourier analysis to model alternating current circuits, breaking complex electrical signals into overlapping sine and cosine waves. This same math reaches up into orbit. This photograph of a rocket launching relies on trigonometric trilateration to calculate precise coordinates as it navigates beyond the atmosphere. Global positioning satellites tracking that rocket, the wireless signals in your smartphone, transmit information using periodic waveforms governed by these exact mathematical rules. The basic ratios of SOH-CAH-TOA serve as the foundational language we use to decode, build, and navigate the physical universe.